September 16, 1943, Bougainville, Solomon Islands. Inside a rough wooden operations hut carved out of the jungle, First Lieutenant Kenneth Walsh paused over his flight log. His hand hovered briefly before he wrote, as if weighing the importance of what he had just experienced in the sky. The aircraft, he noted, had shifted the balance of power. Its speed and firepower finally gave American pilots an edge that Japan's Zero fighters could no longer counter. Yet one problem stubbornly remained unresolved: accuracy. Moments earlier, Walsh had landed his F4U Corsair after escorting Navy bombers through contested airspace. The mission had once again exposed the harsh truth of aerial combat. Even the most capable pilots struggled to hit an enemy aircraft that was actively maneuvering while their own plane twisted violently through the air. Achieving a successful hit required instant calculations of angles, speed, distance, and timing. Calculations no human brain could reliably solve in a split second while under extreme physical stress. Walsh, like thousands of Marine and Navy aviators fighting across the Pacific, had no way of knowing that the solution already existed. Across the Atlantic, British engineers had developed a mechanical answer to this exact problem. By combining spinning gyroscopes with finely calibrated optical systems, they had created an instrument that would soon revolutionize air combat. Within a year, the Mark 18 gyroscopic gunsight would reach the Pacific theater, reshaping aerial gunnery from a skill learned through painful trial and error into a repeatable, teachable science. The F4U Corsair had first seen combat in February 1943, immediately standing apart from earlier fighters. Its massive Pratt & Whitney R2800 double Wasp engine delivered more than 2,000 horsepower, allowing the aircraft to surpass 400 miles per hour. It became the first American single-engine fighter to cross that threshold, giving Marine aviation unprecedented speed. Mounted in its wings were 6 Browning M250 caliber machine guns, each capable of firing close to 800 rounds per minute, an overwhelming volume of fire if the rounds could be placed correctly. And that was the real challenge. Aerial gunnery was not about aiming at where the enemy aircraft appeared to be. It was about predicting where it would be by the time the bullets arrived. This technique, known as deflection shooting, was the most demanding skill a fighter pilot could master. Consider a Corsair flying at 400 mph, attempting to fire on a Japanese Zero, pulling evasive turns at 300 mph. The Corsair's bullets, though leaving the muzzle at roughly 2,700 feet per second, still require precious time to cover the distance. At a range of 500 yards, that travel time approached half a second. In half a second, a Zero executing a standard turning maneuver could shift its position by nearly 200 feet. The pilot had to anticipate that movement, precisely adjusting aim continuously as speed, angle, and distance changed while enduring crushing G-forces that narrowed vision and made clear thinking nearly impossible. A fraction of a second of misjudgment meant every round would pass harmlessly behind the target. Throughout 1943 and into early 1944, Corsairs were equipped with the Mark 8 reflector gunsight. This device offered no mathematical assistance at all. It projected a simple illuminated reticle onto a glass screen, indicating only where the guns were pointed at that instant. The responsibility for calculating lead angles fell entirely on the pilot's experience and instinct. A handful of exceptionally skilled aviators learned to compensate through months of combat. Many others never did. Vast quantities of ammunition were fired across the Pacific skies without result, rounds disappearing into empty space after traveling miles, never touching an enemy aircraft. Kenneth Walsh was among the rare few who mastered deflection shooting through relentless repetition and natural spatial awareness. Flying with VMF 124, he demonstrated an intuitive understanding of three-dimensional motion that could not easily be taught. On May 13, 1943, he became the first Corsair pilot to achieve ace status, destroying 3 Japanese fighters in a single day and bringing his total confirmed victories to 6. Walsh's success came from an ability to sense timing rather than calculate it, to recognize the precise moments when geometry, motion, and opportunity aligned. But pilots like Walsh were exceptions. The average Marine aviator arrived in the combat zone with roughly 200 total flight hours, often with fewer than 20 hours devoted to gunnery practice. Most of that training involved firing at straight-flying towed targets, poor preparation for combat against agile, battle-hardened Zero pilots. Combat reports from 1943 paint a stark picture. Many pilots emptied their ammunition belts without scoring a single hit. Their rounds consistently fell behind maneuvering targets, the result of lead calculations made just a fraction too late. British engineers had confronted this limitation earlier in the war. By 1941, Ferranti had begun manufacturing the Mark II gyroscopic gunsight, a device that fundamentally changed the mechanics of aiming. Its operation relied on a simple physical truth: a spinning gyroscope resists changes to its orientation. When an aircraft turned, the gyroscopes inside the sight attempted to maintain their original alignment as the aircraft rotated around them. This resistance was measured through an intricate system of gears and optical elements. From it, the gun sight determined the aircraft's rate of turn, information directly linked to the amount of lead required to hit a moving target. The sight automatically shifted the aiming reticle forward, placing it exactly where the bullets needed to go, not where the enemy aircraft currently was. For the first time in the history of air combat, the burden of instantaneous mathematical calculation was transferred from the pilot's mind to a machine. When this technology finally reached American fighters in the Pacific, it would permanently alter the outcome of dogfights and the very nature of aerial warfare itself. During the later years of the Second World War, pilots of the Royal Air Force began reporting striking changes in their combat effectiveness after being equipped with a new gyroscopic gunsight known as the Meg-2. Aircrew who had long struggled with the demanding art of deflection shooting, judging where an enemy aircraft would be rather than where it was, suddenly found themselves scoring hits almost immediately after opening fire. What had once required rapid mental calculations under extreme stress was now handled mechanically. Freed from having to solve geometry problems in the middle of a dogfight, pilots could concentrate on positioning, energy management, and tactical decisions. American observers quickly recognized the battlefield significance of this innovation. The technology promised to transform aerial gunnery, and the United States moved swiftly to adopt it. Contracts were awarded to the Sperry Gyroscope Company to manufacture domestic versions of the British design within US service. The Army Air Forces designated their model as the K-14, while the Navy and Marine Corps referred to their equivalent as the Mark 18. Although minor adjustments were made to suit American production methods and cockpit layouts, both sights were fundamentally the same system developed from British combat experience. At the height of wartime output, Sperry's massive facility in Lake Success, New York, employed more than 20,000 workers. Alongside gyroscopic gun sights, the plant produced bomb sights, navigation instruments, and fire control equipment, forming a critical node in the Allied technological supply chain. Compared to the simple reflector sights they replaced, the new gyroscopic units were noticeably larger and heavier. Earlier sights, such as the Mark 8, were compact devices weighing only a few pounds. By contrast, the Mark 18 tipped the scales at roughly 12 pounds and required substantial modifications to aircraft cockpits to accommodate its size and power requirements. According to Sperry engineers, this bulk was unavoidable. Enclosed within the sight housing were two independently operating gyroscopes, each spinning continuously once energized. One measured changes in pitch, the other tracked yaw. Together, they addressed the most persistent challenge in air combat since the First World War, accurately leading a moving target while both aircraft were maneuvering at high speed. The Mark 18 represented the culmination of hard-earned lessons drawn from years of British air combat. The sight's visual presentation was equally sophisticated. Pilots viewed two distinct aiming references simultaneously. A fixed crosshair, positioned to one side, indicated the actual direction of the aircraft's gun bores and served as a constant reference point. Beside it appeared the true innovation, a gyroscopically stabilized aiming symbol composed of a central ring encircled by 6 diamond-shaped markers. This moving reticle represented the calculated point of impact. As the pilot maneuvered to follow an enemy aircraft, the gyroscopic system automatically shifted the reticle ahead of the target, placing it precisely where the bullets needed to go. Operating the system was far simpler than earlier reflector sights, though it still required correct setup. Before engaging, the pilot selected the wingspan of the enemy aircraft using a control on the sight itself, choosing from standardized values based on known Japanese aircraft types. The Mitsubishi A6M0, the most frequently encountered adversary in the Pacific, had a wingspan of approximately 36 feet in its common variants. Once this value was set, the pilot used a twist control integrated into the throttle to adjust the size of the diamond-shaped ranging pattern. By expanding or contracting the reticle until it matched the apparent width of the target's wings, the pilot effectively set the range. This input allowed the sight's internal ballistic system to account for distance and projectile drop. With both range and wingspan established, the mechanical intelligence of the system took over. As long as the pilot maintained a smooth tracking motion, the gyroscopes continuously calculated the required lead angle based on the aircraft's rate of turn. The pilot's task was reduced to a single action: place the computed reticle over the enemy aircraft and fire. Even during complex high-G maneuvers, the bullets would travel to the exact point predicted by the sight. Full-scale production of the K-14 and Mark 18 accelerated in the spring of 1944. Priority initially went to the U.S. Army Air Forces for operations in the European theater. P-51 Mustangs and P-47 Thunderbolts began receiving K-14 installations starting in August of that year. Naval aviation units followed shortly thereafter. The U.S. Navy and Marine Corps scheduled Mark 18 retrofits for F4U Corsairs and fix-F Hellcats throughout the fall and winter of 1944. The earliest Corsair squadrons equipped with the Mark 18 were those preparing for carrier deployment, where precision and rapid engagement were especially critical. Among the first Marine units to receive the new sight were VMF 124 and VMF 213. These squadrons assigned to fleet carriers were introduced to gyroscopic gun sights during advanced training at Naval Air Station Santa Barbara in late 1944. By the time they entered combat, aerial gunnery had been fundamentally reshaped by spinning gyroscopes hidden behind armored glass. By the closing weeks of 1944, a quiet but decisive shift was underway in U.S. naval aviation. Marine fighter squadrons operating the F4U Corsair were preparing to integrate fully into carrier-based warfare, a role the aircraft had long been intended for but had only recently mastered. In December, these squadrons embarked aboard USS Essex, marking the first sustained deployment of Corsairs in frontline carrier combat. Among the pilots was Lieutenant Robert McClure, flying with the reconstituted VMF 214. In early 1945, McClure received a newly issued Corsair fitted with the Mark 18 gyroscopic gun sight, a device that represented a fundamental leap in aerial fire control technology. Having already achieved multiple aerial victories throughout 1944 using the traditional reflector sight, McClure was immediately struck by the transformative nature of the new system. In correspondence sent home to his family, letters that would later be archived by the United States Marine Corps, McClure described the Mark 18 as a dividing line between intuitive estimation and calculated precision. Where pilots once relied on instincts refined through years of combat experience, the gyroscopic sight offered mechanical accuracy governed by mathematics and motion. According to McClure, what previously required extensive combat seasoning could now be learned in a matter of hours. Experience, in effect, had been compressed into machinery. American pilots were not the only ones to recognize the implications. Japanese naval aviation intelligence became aware of the new gunsight technology in late 1944 after examining wreckage recovered from downed Corsairs and reviewing captured technical materials. Their findings were deeply unsettling. The data confirmed that the United States had fielded a fire control system capable of drastically reducing and in many cases eliminating the human error inherent in deflection shooting. Japanese tacticians quickly grasped the significance. This was not an advantage that could be offset through more aggressive training regimes or incremental tactical refinements. The gyroscopes within the Mark 18, spinning at extraordinary speeds, performed calculations beyond the capacity of even the most experienced human pilot. Reaction time, intuition, and visual judgment, once decisive factors in aerial combat, were now being overshadowed by mechanical certainty. Until that point, Japanese fighter doctrine had leaned heavily on superior maneuverability. By forcing American pilots into complex turning engagements and difficult firing angles, Japanese aircraft created situations where even minor miscalculations could mean survival. Against Corsairs equipped with the Mark 18, that buffer no longer existed. If an American pilot could maintain tracking long enough to set the proper range, the probability of a hit became overwhelming, regardless of how violently the target maneuvered. In response, Japanese naval aviation units issued new tactical directives across the board. Pilots were ordered to avoid extended turning battles with Corsairs under any circumstances. Instead, the revised doctrine emphasized brief, high-speed attacks, diving from altitude, making a single firing pass, and disengaging immediately at maximum velocity. This shift was an implicit acknowledgement that agility alone could no longer compensate for technological inferiority in fire control systems. Meanwhile, Corsair operations continued to evolve rapidly. December 1944 marked another historic milestone when VMF 124, commanded by Major William Geezer, became the first Marine fighter squadron to operate from a fleet carrier. Stationed aboard USS Essex at Ulithi, VMF 124 was joined simultaneously by VMF 213, bringing a combined total of 48 F4U Corsairs into carrier service. Both squadrons were fully equipped with the Mark 18 gyroscopic gun sight, placing them at the forefront of American aviation technology. In January 1945, the Essex Air Group launched combat sorties against targets in Formosa and the Philippines. Marine pilots flew a wide range of missions, including combat air patrols, bomber escort, and direct strike operations. At last, the Corsair was performing from carriers in the operational environment for which it had originally been designed. The impact of the Mark 18 became evident almost immediately. Pilots engaging Japanese interceptors consistently reported higher hit probabilities than they had experienced with earlier reflector sights. Combat reports from January and February 1945 record numerous engagements in which enemy aircraft were destroyed during the pilot's first firing burst, a level of immediate lethality that had been relatively rare in earlier phases of the war. The advantage was especially pronounced during bomber escort missions. In these scenarios, Corsair pilots were often constrained by formation discipline, limiting their ability to maneuver into ideal attack positions. Previously, such constraints had reduced engagement effectiveness. With the Mark 18, however, the gun sight's ability to compute accurate deflection solutions from virtually any angle turned these limitations into manageable variables. What had once been tactical disadvantages became viable engagement opportunities. By early 1945, the combination of carrier-capable Corsairs and gyroscopic gun sights had reshaped the dynamics of air combat in the Pacific. The shift was not merely one of aircraft performance, but of philosophy, a transition from combat dominated by human approximation to one increasingly governed by mechanical precision. In that transition, the margin for survival narrowed dramatically for those who lacked the technology to keep pace. By the final year of the Pacific War, aerial combat doctrine was undergoing a quiet but profound transformation. Fighter pilots were no longer required to position themselves directly behind an enemy aircraft at the classic 6 o'clock angle to score a hit. The introduction of advanced gyroscopic gun sights fundamentally altered air-to-air engagements, allowing pilots to fire accurately from crossing angles and complex attack geometries that would have been nearly impossible to calculate using traditional reflector sights. This technological shift became evident in February 1945 during the invasion of Iwo Jima, U.S. Marine Corps squadrons flying F4U Corsairs operated intensively from escort carriers, providing near-constant air cover for the invasion fleet while also supporting ground forces locked in brutal combat ashore. Multiple Marine units rotated through combat air patrols, maintaining a protective umbrella against Japanese air attacks throughout the operation. Aircraft equipped with the Mark 18 gyroscopic sight quickly proved their worth. During defensive interceptions, Marine pilots consistently engaged enemy aircraft at distances and angles that would previously have required extreme skill or sheer luck to succeed. The sight's automatic deflection computation relieved pilots of the need to mentally calculate lead angles in the heat of combat. As a result, engagements became faster, more efficient, and far deadlier. The practical effects were striking. Where a pilot using an older reflector sight might expend an entire ammunition load attempting to down a single evasive target, Corsair pilots flying with the Mark 18 were often able to damage or destroy multiple aircraft during a single encounter. This ability to shift rapidly between targets while maintaining accuracy not only conserved ammunition but dramatically increased each pilot's effective combat output. Operational reports from Marine squadron commanders repeatedly emphasized another unexpected benefit: the narrowing of the performance gap between veterans and newcomers. Less experienced pilots were achieving kill rates and engagement success comparable to seasoned aces, largely due to the improved fire control precision offered by the gyroscopic sight. Technology in this case acted as a force multiplier that elevated the entire squadron's effectiveness. Carrier operations continued into March 1945 as American forces intensified strikes against the Japanese home islands. VMF 214, operating from the fleet carrier USS Franklin, participated in sustained attacks against enemy airfields and military infrastructure. On March 19th, while conducting operations near Kyushu, Franklin was struck by a Japanese bomber. The resulting explosions ignited catastrophic fires that swept through the ship, killing more than 700 sailors and aircrew. Among the dead were 32 members of VMF 214. The squadron was effectively shattered, suffering losses that would have crippled many units, yet those who survived continued flying missions after the heavily damaged carrier was brought to safety. The tragedy underscored the extreme risks of carrier warfare and the extraordinary resolve demanded of the men who operated from floating airfields under constant threat. Despite these losses, Marine Corsair squadrons remained fully committed to their mission. Their role as both fleet defenders and strike aircraft became even more critical as the war approached its final and bloodiest phase. In April 1945, Operation Iceberg, the invasion of Okinawa, began. This campaign marked the most intense period of kamikaze warfare in history. Facing imminent defeat, Japanese forces launched thousands of aircraft in deliberate suicide attacks against the American fleet in a desperate attempt to disrupt the invasion. Marine Corsairs armed with Mark 18 sights were central to countering this threat. Kamikaze aircraft typically followed predictable attack paths, diving directly toward their targets. These profiles played directly into the strengths of the gyroscopic sight. Pilots could quickly lock on to incoming attackers, adjust range using the sight's ranging reticle, and deliver accurate fire with their first burst, something rarely achievable with earlier sighting systems. Throughout April, May, and June of 1945, combat air patrols over Okinawa and the surrounding waters resulted in the destruction of hundreds of Japanese aircraft. While declassified records do not provide exact figures distinguishing kills achieved by gyroscopic-equipped fighters versus those using reflector sights, contemporary after-action reports consistently highlighted superior performance among squadrons that had received the Mark 18. Beyond its tactical impact, the psychological effect of this technology was profound. Japanese pilots who survived encounters with Mark 18-equipped Corsairs described a deeply unsettling experience. Evasive maneuvers that once offered a chance of survival no longer seemed effective. Tracer rounds appeared to arc through the sky with unnatural precision, striking aircraft regardless of defensive action. Post-war interviews with Japanese aviators revealed that advanced American fire control systems ranked among the most demoralizing technologies they faced. Once an American pilot achieved a stable tracking solution, escape felt impossible. This sense of technological inevitability stripped away the fragile hope that had sustained Japanese fighter pilots as the strategic situation deteriorated. By the final months of the war, the Mark 18 gyroscopic sight had become more than a technical improvement. It was a decisive factor in air superiority. It reshaped aerial combat, amplified pilot effectiveness, and contributed significantly to the overwhelming dominance of Allied air power in the Pacific's closing battles. By the later stages of the war, agility alone was no longer enough to guarantee survival in the air. Veteran pilots discovered that experience, while still valuable, could no longer compensate for the realities of modern aerial combat. In many situations, avoiding combat altogether was the only true defense. An option that simply did not exist when fighters were tasked with intercepting enemy bombers or shielding friendly ships below. It was in this unforgiving environment that the Mark 118 gunsight emerged as a quiet technological revolution. Its internal workings stood as one of the most impressive examples of mechanical problem-solving ever fielded in combat aviation. Without relying on electronics of any kind, the system performed complex predictive calculations using only precisely engineered metal components. Tasks that would have taxed even a skilled mathematician working by hand. Once powered, the sight's gyroscopes spun continuously, preserving their fixed orientation in space through angular momentum. As the aircraft rolled, climbed, or turned, the surrounding housings shifted around these stable rotors. This relative movement was captured by finely cut gears, which translated motion into adjustments of internal mirrors. Those mirrors, in turn, shifted the position of the aiming reticle, automatically accounting for lead, speed, and angular change. Every part of the system functioned within tolerances measured in mere thousandths of an inch. Built in 1944 using the most advanced machining methods then available, the production lines at Sperry represented the height of American precision manufacturing. Each individual Mark 1118 sight consisted of dozens of carefully machined components, all of which had to meet strict specifications to function reliably as a unified system. The gyroscopes themselves were engineering marvels. Compact, high-speed rotating assemblies designed to operate smoothly despite constant vibration and aggressive maneuvering. They had to maintain flawless performance during prolonged high-G flight without seizing, drifting, or wearing unevenly. Achieving that level of reliability demanded exceptional craftsmanship and rigorous inspection. Before leaving the factory, every completed sight underwent extensive testing. Specialized test rigs replicated the movements of an aircraft in combat, subjecting the system to varying turn rates, speeds, and simulated target distances. Engineers verified that the sight correctly calculated deflection under all expected conditions. Units that failed to meet standards were disassembled, adjusted, or completely rebuilt until they performed flawlessly. The challenge facing Sperry was not only technical excellence but scale. Thousands of aircraft across multiple theaters required these sights, often under tight timelines. Throughout 1944, production was steadily increased, and workers were trained in the highly specialized skills needed for optical alignment and precision mechanical assembly. The Mark 1118 successfully combined mass production efficiency with the uncompromising standards demanded by a precision instrument. Components were engineered to be interchangeable, allowing parts manufactured at separate facilities to be assembled seamlessly into finished units. This modular design proved invaluable in combat zones, where maintenance crews could replace individual failed components instead of removing entire sites from service. To support frontline operations, spare parts were distributed throughout Pacific maintenance depots. If a site malfunctioned during combat operations, technicians could quickly restore functionality, minimizing aircraft downtime and preserving combat readiness. Integrating the Mark 118 into the cockpit of the F4U Corsair required careful attention to human factors. The sight had to sit naturally within the pilot's field of view, allowing him to maintain awareness of the surrounding airspace. Equally important was the throttle-mounted range control, which needed to be adjustable without forcing the pilot to remove his hand from essential flight controls. Engineers collaborated closely with experienced combat pilots during installation trials. Their feedback shaped refinements that addressed visibility, control placement, and usability during high-stress engagements. The final configuration allowed pilots to operate the sight instinctively without diverting mental focus from tactical decisions or aircraft control. Effective use of the Mark 118 also required dedicated training. Instruction focused on helping pilots understand what the sight was indicating and when its calculations could be trusted. They learned how to recognize when the gyroscopes had stabilized after abrupt maneuvers and how to set target range quickly using the distinctive diamond-shaped ranging display. Ground instruction introduced the basic concepts behind gyroscopic deflection calculation, deliberately avoiding excessive mathematical detail. The objective was operational competence, not technical mastery. Pilots needed confidence in using the system, not the ability to engineer it. In the air, training flights included simulated intercepts against target aircraft. These exercises allowed pilots to experience firsthand how the sight responded during real tracking scenarios. Instructors emphasized smooth, controlled pursuit, noting that erratic maneuvering could temporarily degrade accuracy. The system performed best when the aircraft maintained a steady turn, giving the gyroscopes consistent motion to measure. Pilots were also taught to respect the sight's limitations. After violent control inputs or sudden reversals, the gyroscopes required a brief moment to restabilize. During that interval, the reticle would lag before once again providing accurate deflection guidance. Understanding these behaviors was essential to using the Mark 118 effectively and to trusting it at the precise moment when accuracy mattered most. Experienced aviators quickly learned that the new fire control system was not without constraints. Rather than relying on it blindly, they adapted their combat techniques, choosing to initiate attacks during moments when the system had settled into stable operation. This practical understanding allowed pilots to extract maximum effectiveness while minimizing potential disruptions during critical seconds of engagement. Even with these minor operational drawbacks, the Mark 118 marked a dramatic turning point in the evolution of aerial fire control systems. For many pilots, especially those accustomed to traditional reflector sights, the change was profound. Techniques like deflection shooting, once dependent on instinct, experience, and exceptional hand-eye coordination, became far more consistent. Hits that had previously been rare or accidental began to occur with surprising regularity. The new sight did not eliminate the inherent dangers of air combat. Dogfighting remained an unforgiving environment that demanded sharp tactical thinking, constant situational awareness, and precise aircraft handling. However, it fundamentally altered one critical element of combat: the act of firing. The precise moment when a pilot squeezed the trigger was no longer governed solely by estimation and guesswork. Instead, it became a more controlled, repeatable, and ultimately deadlier process. Assessing the overall influence of the Mark 118 on Corsair operations during 1945 is challenging. Surviving wartime records do not provide enough granularity to isolate its direct impact. What is available are broad statistical summaries that reflect the combined performance of aircraft equipped with various sighting systems throughout the war. According to official U.S. Navy and Marine Corps records, F4U Corsair units achieved an aggregate air-to-air victory ratio of approximately 11-to-1 during World War II. Across more than 64,000 combat sorties, Corsair pilots claimed over 2,000 confirmed aerial victories while suffering fewer than 200 losses to enemy fighters. These figures encompass aircraft using both older reflector sights and later gyroscopic systems, making it impossible to attribute success solely to the Mark 118. A precise breakdown would require access to detailed mission reports and engagement analyses, many of which remain classified, incomplete, or lost to history. In the absence of such data, historians have relied heavily on first-hand pilot accounts. These personal testimonies present a remarkably consistent picture. Pilots who flew with both sighting systems overwhelmingly agreed that the Mark 118 transformed deflection shooting from an art into a skill that could be learned and repeated. Success no longer depended entirely on natural talent or years of combat seasoning. Instead, the sight leveled the playing field, allowing competent pilots to perform at a higher and more reliable standard. Supporting evidence appears throughout squadron diaries, operational summaries, and post-war memoirs. Again and again, aviators described the gyroscopic sight as a decisive advantage, one that reduced uncertainty during high-speed engagements and increased confidence during fleeting firing opportunities. Beyond its combat effectiveness, the Mark 118 represented a broader achievement in American wartime engineering. It combined advanced gyroscopic stabilization, precision optics, and mechanical computing into a compact, rugged device capable of surviving vibration, temperature extremes, and battle damage. Just as importantly, it could be produced in large numbers. Thousands of units were manufactured, shipped across vast distances, and maintained at forward airfields by technicians working under harsh and often improvised conditions. The program's success did not hinge on a single breakthrough. Instead, it reflected a system that worked end-to-end from scientific theory to industrial production to battlefield maintenance. The original concept emerged from British research. American engineers refined the design to suit mass manufacturing. US industry produced the units at scale, and American logistics ensured they reached squadrons scattered across the globe. The Mark 118 became a textbook example of the systematic, industrialized approach that defined American wartime technology development. In the years following the war, Japanese aviators and military analysts began reassessing Allied fire control systems through memoirs, interviews, and historical studies. Their conclusions were strikingly uniform. By late 1944 and into 1945, American advances in fire control technology had undermined the effectiveness of Japanese aerial tactics. Even highly maneuverable aircraft flown by experienced pilots struggled to compete against opponents equipped with systems that automatically calculated firing solutions. Traditional doctrine, built around agility and pilot skill alone, could no longer offset the technological gap. These lessons left a lasting imprint on Japan's post-war aviation philosophy. When the Japan Self-Defense Force was formed in the 1952, its development priorities shifted decisively. Rather than focusing primarily on aircraft maneuverability, emphasis was placed on advanced avionics, integrated weapons systems, and technological superiority. An approach shaped directly by wartime experience with systems like the Mark 118. Pilots who had lived through air combat against Corsairs equipped with the Mark 18 gyroscopic sight came away with a clear realization. The future of aerial warfare would be shaped less by raw flying talent and more by the machines that supported it. Individual skill still mattered, but technology was rapidly becoming the decisive factor. The F4U Corsair itself proved to be far more than a wartime stopgap. Its operational career extended well beyond the end of World War II. During the Korean War, from 1950 to 1953, Marine Corps squadrons continued to fly the aircraft in combat, using it extensively for close air support and deep interdiction strikes. Remarkably, many of these Corsairs still carried the same Mark 18 gyroscopic gunsights that had seemed so advanced just a few years earlier. By the early 1952s, what had once been cutting-edge innovation had faded into the background of routine military equipment. The Mark 18 was no longer a novelty, it was simply expected. This quiet acceptance of sophisticated technology defined the post-war period. Capabilities that would have appeared fantastical in 1940 became standard practice by 1950, and within another decade, many were already considered outdated. The evolution of aerial gunnery followed a similar path. What had once been regarded as a near art form, dependent on instinct and countless hours of practice, was increasingly transformed into a technical process governed by mathematics and mechanical computation. The introduction of the Mark 18 accelerated this shift, pushing air combat toward its eventual endpoint. Weapons systems that removed the act of aiming from the pilot entirely. The arrival of air-to-air guided missiles in the 1952s marked a fundamental break from earlier traditions. Pilots no longer needed to maneuver their aircraft precisely to align guns with a moving target. Instead, missiles could be launched based on sensor data and guidance systems, allowing engagement from angles and distances previously impossible. In less than 15 years, aviation had progressed from simple reflector sights to gyroscopic systems and then to radar-guided weapons. A rate of change unmatched in the history of military flight. By the time American aviators flew combat missions over Vietnam in the 1960 seconds, the core ideas behind the Mark 18 were embedded within vastly more complex fire control computers. These systems combined radar distance measurements, automatic lead calculations, ballistic corrections, and target tracking into integrated electronic networks. Compared to these digital assemblies, the Mark 18's mechanical components seemed almost primitive. Yet beneath the layers of added complexity, the underlying logic remained the same. Measure the motion of the aircraft using gyroscopes, determine the necessary lead angle, present that solution to the pilot in a way that makes accurate fire achievable under combat conditions. This fundamental approach, pioneered during World War II, continued to define aerial weapons design for decades. To understand the Mark 18's real impact, it must be viewed within the broader record of Corsair combat operations. From 1943 to 1945, Marine and Navy squadrons flew tens of thousands of sorties against Japanese forces across the Pacific. Over the course of these campaigns, the Corsair achieved an impressive kill ratio of approximately 11 enemy aircraft destroyed for every loss suffered. This outcome was not the result of a single advantage, but rather the convergence of several strengths. The Corsair's superior speed allowed pilots to dictate the terms of engagement, choosing when to attack and when to withdraw. Its rugged airframe could withstand damage that would have brought down lighter, more fragile opponents. Its heavy armament delivered devastating firepower when hits were achieved. The Mark 18 gyroscopic sight did not create these advantages, but it made them easier to exploit. By simplifying deflection shooting, it increased the likelihood that the Corsair's firepower would actually connect with its target. Accuracy improved not because pilots suddenly became better tacticians, but because one of the most difficult technical challenges of aerial gunnery had been partially automated. Even so, human skill remained indispensable. The Mark 18 could not teach judgment, situational awareness, or tactical decision-making. These qualities still depended on training and combat experience. What the sight accomplished was a narrowing of the learning curve for a specific and demanding skill that had previously taken years to master. Placed in historical perspective, the Mark 18 was one element within a much larger framework of American technological dominance during the Pacific War. Radar networks provided early warning and guided intercepts. Reliable radio communication enabled coordinated air and naval operations. Proximity-fused anti-aircraft ammunition transformed shipboard defense. Each system offered its own advantage, but together they formed a tightly interconnected whole that Japanese forces were unable to counter effectively. Within this ecosystem, the Mark 18 was not a miracle device that single-handedly decided the air war. It was a practical refinement, an improvement in fire control efficiency that amplified the effectiveness of already capable aircraft and well-trained pilots. Its impact was incremental rather than dramatic, but when multiplied across thousands of aircraft and countless combat encounters, those small gains accumulated into a meaningful strategic effect. The sight's legacy also extended beyond the battlefield. Its development marked a new model of collaboration between scientists, engineers, and combat personnel. Physicists contributed theoretical insights into gyroscopic behavior. Manufacturing specialists solved the challenges of mass production. Fighter pilots provided feedback that drove continuous refinement. Together, they demonstrated how modern warfare was increasingly shaped not just by bravery or skill, but by the systematic integration of science, industry, and operational experience. The development of the Mark 18 gunsight became more than a single technical success. It set a lasting example for how advanced weapons could be created through international cooperation. Instead of insisting on reinventing every component domestically, the United States chose a more practical path. British breakthroughs in fire control technology were acknowledged, refined, and integrated into American industrial systems. This openness to adopting foreign innovations when they clearly offered operational advantages reflected a pragmatic mindset that continued to shape U.S. military aviation throughout the Cold War and well into the modern era. The influence of the Mark 18 extended far beyond its immediate combat role. The production methods devised by Sperry for manufacturing the system reshaped American defense industry practices. By dividing the sight into standardized, interchangeable modules that could be built at different factories, Sperry enabled output on a scale few nations could match. These modular manufacturing principles were later applied to radar installations, aircraft propulsion systems, and eventually electronic equipment. Over time, they helped establish an industrial foundation capable of producing highly complex, precision technologies in enormous quantities. One of the defining advantages of American military power in the mid-20th century. The pilots who first relied on the Mark 18 represented a transitional generation in aerial warfare. Many of them had begun their careers depending almost entirely on instinct, experience, and visual judgment. Now, they were learning to integrate mechanical computation into split-second combat decisions. This shift did not replace skill, but it fundamentally changed how air combat was approached. Numerous pilots carried these experiences into long military careers, flying early jet aircraft during the Korean War and later serving in command and planning roles. There, they helped craft new tactical doctrines built around increasingly sophisticated fire control systems. One such figure was Lieutenant Kenneth Walsh. In 1943, flying the F4U Corsair, Walsh became the aircraft's first ace using nothing more than a reflector sight and exceptional natural ability. By the end of the Second World War, he had accumulated 21 confirmed aerial victories. His courage was formally recognized when he was awarded the Medal of Honor for actions on August 15, 1943. Despite flying a damaged aircraft, Walsh repeatedly attacked a numerically superior formation of Japanese fighters, breaking up their assault through sheer determination and tactical skill. Walsh survived the war and continued his service in the United States Marine Corps, eventually retiring with the rank of lieutenant colonel. His career neatly mirrored the evolution of aerial combat itself, from close-range dogfights dominated by machine guns to an era defined by guided missiles and advanced targeting systems. What he experienced firsthand was not merely technological progress, but a fundamental transformation in how wars were fought in the air. Another example of this generational shift was Lieutenant Robert McClure, who flew with the reactivated VMF 214 Squadron in 1945. McClure completed the war with 7 confirmed victories and remained in the Marine Corps until his retirement in 1965 as a colonel. In later years, he reflected extensively on the changes he had witnessed. While he acknowledged that the Mark 18 made deflection shooting more consistent and reliable, he was careful to dispel any illusion that it made air combat safe or simple. According to McClure, the gun sight reduced only one element of uncertainty. Many others remained untouched. A pilot still had to manage altitude and speed, maintain awareness of threats, and position the aircraft advantageously. Tactical judgment, energy management, and situational awareness continued to determine survival. Even with a perfectly calibrated sight, an aircraft could be outclimbed, outturned, or ambushed by an unseen opponent. Technology improved effectiveness during engagements, but it offered no guarantees. The story of the Mark 18 does not conclude with a dramatic moment of obsolescence. Instead, it fades gradually into the broader arc of technological evolution. As jet fighters replaced propeller-driven aircraft in the 1950 seconds, new generations of fire control systems emerged, better suited to higher speeds and longer engagement distances. The Mark 18 did not suddenly fail. It was simply overtaken by the demands of a new era. Some units remained in operational use for a time, particularly on Corsairs flying close air support missions during the Korean War. Others were placed into storage or dismantled as older aircraft were phased out. A small number survived intact and found their way into museums, where they remain tangible reminders of a period when mechanical computing stood at the cutting edge of military technology. Today, the Mark 18's true legacy lies not in surviving hardware, but in the principles it introduced. Modern fire control systems, no matter how digital or advanced, trace their conceptual roots back to early solutions like the Mark 18 that first addressed the challenge of automated aiming. The engineers behind the system proved that complex calculations could be performed mechanically with sufficient speed and reliability for combat conditions. they demonstrated that human-machine interfaces could be designed for use under extreme stress. They also showed that advanced technology could be mass-produced and maintained in harsh operational environments. The pilots who flew with the Mark 18 contributed just as much to its legacy. Through combat use, they tested its limits, identified its weaknesses, and shaped improvements through direct feedback. In doing so, they helped develop tactics that bridged the gap between human judgment and mechanical assistance. Together, the engineers and airmen of the Mark 18 era laid the groundwork for the modern age of aerial warfare, an age where technology enhances capability but never replaces the human element at the heart of combat. At its core, the development of the Mark 18 demonstrated something far more enduring than a single wartime innovation. It showed that humans and machines could work together effectively without one replacing the other. Pilots did not surrender their judgment to automation, nor did they dismiss technology as unnecessary. Instead, the system encouraged cooperation, blending human decision-making with mechanical calculation. This balanced relationship between operator and machine continues to matter today, as automated systems increasingly enter new fields far beyond aviation. The period in which the Mark 18 emerged provides valuable historical lessons about why such partnerships succeed. The gyroscopic gunsight does not merit remembrance because it was a dramatic breakthrough, nor because it alone reshaped the outcome of the Pacific War. Its significance lies elsewhere. The Mark 18 stands as an example of a quieter kind of progress, the disciplined, methodical work of solving real problems in practical ways. Modern culture often glorifies sudden revolutions and disruptive inventions. The Mark 18 tells a different story. It reminds us that gradual refinements, when carefully engineered and deployed on a large scale, frequently deliver greater real-world impact than bold ideas that cannot be reliably built, supplied, or used. The system succeeded not because it was elegant or revolutionary, but because it was dependable, functional, and effective enough to matter where it counted most. Those qualities, reliability, usability, and practicality, are rarely celebrated, yet they define technologies that genuinely change outcomes. The Mark 18 worked in harsh combat environments. It could be mass-produced without crippling industrial bottlenecks, and it could be learned by pilots without months of specialized instruction. These unglamorous attributes proved far more valuable than theoretical perfection. Ultimately, the Mark 18 is not just a story about machinery, it is a story about people. Engineers translated combat needs into mechanical solutions. Factory workers assembled thousands of units. Logistics teams ensured the sites reached the front lines. Maintenance crews kept them functioning under demanding conditions. Pilots learned to trust and use them in combat. Commanders incorporated them into broader operational doctrine. Each role was indispensable. Had any one of these groups failed, the entire program would have faltered. This interconnected effort highlights a truth that often goes unnoticed in technological history. While individual brilliance has its place, coordinated work across institutions and professions is what determines success. The Mark 18 was the product of thousands of individuals performing their duties with consistency and competence, rather than a single moment of genius. When evaluating the impact of the Mark 18, it is essential to separate what can be firmly documented from what remains uncertain. Archival records confirm that the sight was produced in large quantities and installed on many Corsair and Hellcat aircraft during the final years of the war, particularly in 1944 and 1945. Pilot evaluations consistently praised the system, noting improvements in aiming efficiency and reduced time needed to engage enemy aircraft. Combat reports from squadrons equipped with gyroscopic sights suggest better firing accuracy and faster engagements. First-hand accounts from pilots describe the Mark 18 as a major improvement over traditional reflector sights, especially for deflection shooting against maneuvering targets. However, what cannot be conclusively measured using declassified data is the precise numerical increase in kill ratios attributable solely to the gun sight. Factors such as pilot experience, evolving tactics, and the declining effectiveness of Japanese opposition complicate any attempt at exact statistical attribution. The widely cited overall Corsair kill ratio of approximately 11:1 reflects performance across the entire conflict and includes aircraft equipped with multiple sighting systems. Still, the available evidence leaves little doubt that the Mark 18 represented a meaningful advancement in aerial fire control technology. It provided pilots with a tangible advantage and reflected the broader strengths of American wartime industry. Large-scale manufacturing, applied innovation, and systematic problem-solving. As aerial combat evolved from individual instinct toward integrated technological systems, the Mark 18 marked a transitional moment. It arrived at a time when human skill alone was no longer sufficient to meet the demands of increasingly fast and complex air battles. By allowing machines to handle rapid calculations more quickly and consistently than the human mind, the system pointed toward a future where automation would play a central role. That future arrived sooner than many realized. The Mark 18 bridged the gap between traditional gunnery and the age of radar-guided missiles. It represented both an endpoint and a beginning, the final refinement of mechanical fire control methods and the conceptual foundation for the electronic systems that followed. Its influence can still be traced today in the computerized targeting systems of modern combat aircraft, descendants of the spinning gyroscopes that first taught machines how to aim. For the pilots flying Corsairs in 1945, the Mark 18 was not a symbol of technological revolution. It was simply a reliable tool that made an already dangerous job slightly less unforgiving. It did not remove risk or guarantee survival, but it improved the odds in a form of combat where small margins often determined life or death. The oft-repeated observation that Japanese forces did not anticipate gyroscopic sights turning Corsair pilots into precision marksmen captures the broader meaning of the story. It is a narrative of necessity, driving innovation, of engineering responding to combat realities, and of ideas succeeding only when matched with effective implementation. In the Pacific theater, American industrial capacity and organized problem-solving reshaped aerial warfare not through a single dramatic invention, but through countless practical improvements applied consistently. The Mark 18 gyroscopic gun sight stands as one of those improvements, quiet, mechanical, and profoundly influential, advancing the art of air combat, one rotating gyroscope at a time.